All right, let's get right into it. When you picture the invention of pottery, what's the first thing that pops into your head?
You know, for the longest time, the story we all learned was simple and it was logical. Humans settle down, they start farming, they've got all this grain, and they need somewhere to store it. Boom, they invent pottery. It just makes sense, right? I mean, why would a hunter-gatherer always on the move want to lug around heavy, super fragile clay pots?
But here's the thing. That whole idea, it's been completely turned on its head. The very first people to truly master fire and earth, they weren't farmers, not even close. They were nomadic hunters, living deep in the Ice Age, chasing mammoths across the frozen plains of ancient Europe. Okay, so our first piece of evidence that just blows up that old timeline is this one single, absolutely extraordinary object found in what's now the Czech Republic. It is such an anomaly that it forces us to rethink everything we thought we knew about our Stone Age ancestors.
Just look at that date, 29,000 BCE. That's when the first known ceramics were made. We're not talking 10,000 years ago with the first farmers. We're talking nearly 30,000 years ago. Deep, deep in the Ice Age. It's just a staggering leap back in time.
So, what was this first ceramic masterpiece? It wasn't a bowl, it wasn't a storage jar. It was this, the Venus of Dolnivie Sonice. It's a small, stylized statuette of a woman made by a culture of really sophisticated mammoth hunters that we call the Gravetians. And the crucial part is, it wasn't made for storing food. It was made for something else entirely. And let me tell you, this was no happy accident. Creating the Venus shows such a deep understanding of materials, of heat, of process. These Ice Age hunters weren't just artists. You could call them the world's first ceramic engineers. And their incredible technology seems to have served a spiritual or ritual purpose. The recipe they used is just fascinating. They took local soil, a type called loess, and mixed it with water. Simple enough, but here's the secret ingredient, ground up mammoth bone. This acted as what's called a temper. It's an additive that strengthened the clay and, most importantly, kept it from cracking and shattering in the kiln. This is an incredibly advanced multi-step process for the time. And this just shows their complete mastery of fire. I mean, they were firing these little objects at up to 800 degrees Celsius. That is hot enough to permanently change the clay's chemical structure, a process called vitrification, which is literally turning clay into rock. But it's still a temperature you could manage in a primitive kiln. They could even control the atmosphere inside the kiln. It's just staggering. And this wasn't some one-off experiment. Archaeologists have found over 5,000 ceramic fragments at this one site. That points to a dedicated production center, like a kind of Ice Age kiln complex, where this was happening again and again. This was a core part of their culture. So why make thousands of them? Well, here's where it gets really wild. A lot of these fragments show signs of thermal shock, which suggests they were tossed into the fire while they were still wet. The leading theory is that these figurines were actually made to be destroyed, to ritually explode in the fire, maybe as part of some dramatic ceremony or a divination ritual. The process, that explosive transformation, might have been the whole point, not the finished product. Okay, so now let's jump to a completely different part of the world, because while all of this ritual explosion was happening in Europe, ceramics were being invented, again, completely independently in East Asia, but for a totally different reason. This timeline shows another Ice Age origin for pottery, this one kicking off around 20,000 years ago in China. And these were not figurines. These were coarse, thick-walled jars and cauldrons, the world's first actual pots. And once again, this is all happening thousands and thousands of years before the first farms ever appeared in that region. So that brings us back to the question, why would Ice Age hunters bother with heavy, breakable pots? And the answer is incredibly simple: survival. During the last glacial maximum, one of the harshest periods in human history, the cooking pot was nothing short of a revolutionary tool. Seriously, you cannot overstate the power of a pot in an Ice Age world. It let people boil bones to get every last calorie of grease and marrow out. It could detoxify plants, opening up whole new food sources. It could make life-saving broth from scraps, making sure that absolutely nothing was wasted. This one piece of tech gave them a massive survival advantage, an advantage so huge it was worth the hassle of carrying it around. So what we're looking at are two completely independent births of ceramic technology. They're separated by thousands of miles and driven by totally different needs. In Europe, a spiritual or symbolic motive led them to make figurines. In East Asia, the raw need for survival led them to make cooking pots.
Two very different problems, but one revolutionary solution: fired clay.
When you zoom out, the invention of ceramics represents something truly profound in the human story. It's so much more than just art or cooking. It really marks the dawn of our ability to fundamentally change the material world around us.
Think about it. Before this, what did we do? We shaped things that already existed. We carved wood. We chipped away at stone. But with ceramics, for the very first time, we took a material, soft, mushy, water-soluble earth, and through a controlled process of heat, we transformed it into something entirely new, a hard, waterproof, permanent solid. This is the birth of material science. I just love this quote. It perfectly captures the absolute magic of that moment. It was our species' first real act of alchemy, the transmutation of mud into stone. That is the moment we stopped just using the world and started remaking it.
And this slide just illustrates the long-term impact so perfectly. That simple, incredible ability to turn Earth into rock became the foundation for, well, everything. From the bricks that built our first cities and the pipes that carried clean water, to the insulators that carry our electricity, and even the silicon in our computer chips, it all traces back to this one innovation: our ancestors transforming mud into stone.
So to really get why the pot was such a big deal, you have to picture what life was like before it. This right here, this is the before picture. Life was incredibly vulnerable. You were nomadic, always on the move, because any food you found would spoil pretty quickly. There was no pantry, no fridge, no security net. But pottery was about to flip this entire script and create a totally new after picture for humanity. The breakthrough itself seems almost laughably simple, right? You take some clay from the ground, you shape it, you fire it, and boom, you've got a vessel. But this wasn't just another tool. This was, and I'm not exaggerating here, the world's very first bank vault. What it allowed for is something called time shifting of caloric consumption. It sounds super technical, I know, but the idea is powerful. For the very first time, you could harvest a bunch of grain in the fall and still be eating it in the middle of a freezing winter. That relentless hand-to-mouth cycle of feast or famine, it was finally broken. And you have to understand, fired clay was a massive technological leap forward. I mean, think about it. A woven basket, it leaks. A pit in the ground, bugs and water get in. But a ceramic pot, it's waterproof, it's rodent-proof. It creates this perfectly sealed, safe environment. It was the ultimate security system for humanity's most valuable asset, its food. And that's why this whole bank vault idea is so perfect. People weren't storing gold or jewels, they were storing calories. Literally, the currency of life itself. And for the first time, you could save that currency. You could build up wealth. You could actually invest in your own future. And this is where it gets really wild. This one, simple ability to store grain, kicks off this incredible domino effect. First, secure storage means you can create a food surplus. More food means you can support more people, so the population grows. And once you have a larger, stable population with plenty of resources, well, now you can start building villages, towns, and complex societies. It's the basic recipe for civilization, and it all starts with a pot. Of course, you know how this goes. The second you have wealth, you get power dynamics. Those huge clay jars filled with grain, they were capital. And whoever controlled the storage, whoever controlled the pots, well, they controlled the power. This is the moment we start to see the beginnings of social hierarchies and centralized control. But believe it or not, storage was only half the story. The pot had this other, totally unexpected superpower. It wasn't just a vault for keeping things safe. It was also a laboratory. It was about to kickstart a whole other revolution: fermentation. And we have the receipts. It's amazing. Archaeologists can analyze these things called lipid residues, basically microscopic bits of ancient fat that's soaked into the porous clay. In China, they found evidence of rice fermentation, yeah, that's beer, going all the way back to 7,000 BCE. In Europe, thousands of years later, they found residue from dairy processing, like making cheese and yogurt. This pot was the original multi-tool. And really, it all boils down to something this simple. If you want to make beer or wine or pretty much any fermented drink, you absolutely have to have a liquid-tight container. It's just not possible otherwise. The ceramic pot created the perfect little chemistry lab for yeast to do its magic. No pot, no beer. It's as simple as that. So thanks to this incredible scientific detective work, we can look at these ancient pottery shards and know what people were eating and drinking thousands of years ago. We see evidence for beer and wine, for yogurt and cheese, even for things like preserved fish. It paints this incredibly rich and, frankly, delicious picture of the Neolithic menu. And look, this wasn't just about having a party. These fermented drinks became critical to the fabric of society. They were the fuel for huge ritual feasts that brought entire communities together. They were a tool for social bonding. And if you could brew a surplus of really good beer, well, that was a super valuable item for trade and for forging alliances with your neighbors. So when you step back and look at the whole picture, the legacy of the pot is just so much bigger than being a simple container. This one invention, this humble piece of baked clay, fundamentally re-engineered human society from the ground up. It all comes down to these four pillars, really. The pot gave us surplus, breaking that hand-to-mouth existence. That surplus gave us stability, letting us settle down in one place. That stability became the foundation for complex society, creating wealth and social structures. And finally, it gave us celebration, new ways to come together through ritual and social bond.
This is the story of how a simple block of baked mud became one of the most important inventions in all of human history. Wow, that quote really just says it all, doesn't it? The story of the brick isn't just about architecture. It's about how we, as a species, learned to build a permanent world, how we figured out how to house entire societies. It's our story of going from something temporary to something truly eternal.
So, where does this whole journey kick off? Well, like a lot of great stories, this one starts with something, well, really simple. It starts with mud. The very first bricks, which showed up thousands of years ago in places like Jericho, were basically just patties of mud. People would just grab a handful, shape it, and leave it out to bake in the sun. Now, these Adobe-style bricks, they worked okay, as long as you were in a really dry climate. But they had one massive, fundamental flaw.
Exactly. I mean, think about it. Sun-dried mud is just dried mud. It's incredibly vulnerable to moisture. One heavy rainstorm, one seasonal flood, and your entire building could just dissolve. Your city could literally melt back into the earth it came from. So yeah, a more permanent solution was definitely needed.
And what's so fascinating is that the first huge leap forward wasn't what you'd expect. It wasn't about heat, it was about geometry. Early civilizations in Mesopotamia and Egypt came up with a simple tool that changed everything: a wooden mold. And man, what a difference it made. This was a total game changer. You go from these lumpy, irregular, hand-molded patties to standardized blocks that all have the same dimensions. And that means you can suddenly create stable, interlocking patterns, build stronger walls, and do it all way faster. You're not just stacking mud pies anymore, you're actually engineering a structure.
And we even know exactly how they did it, which is amazing. We have these ancient Egyptian tomb paintings that show the whole process like an assembly line. You see workers mixing clay with straw, which acts as a binding agent to stop cracking, then pressing that mix into those all-important wooden frames and laying them out to dry. It's a standardized, almost industrial process. But you still have that same old problem, right? Water.
And this brings us to the next phase, the moment the brick goes from being temporary to being truly permanent. This is the moment we add fire to the equation.
So, around 3500 BCE, somebody had a brilliant idea. They figured out that if you bake bricks in a super hot oven called a kiln, you could fundamentally change the material itself. This was huge, especially for river valley civilizations like Mesopotamia and the Indus Valley, because they didn't have big stone quarries like the Egyptians did. They had to make their own rock. Now, the science behind this is a process called vitrification. It sounds complicated, but the idea is actually pretty simple. When you get clay hot enough, the silica, which is basically sand, that's inside it literally melts and turns into a kind of glass. This fuses all the clay particles together, and it creates a material that's no longer porous. It becomes waterproof and incredibly strong. And that right there is the magic trick. Through this process, humans took simple mud from the ground and transformed it into a building material as strong and durable as stone. They literally invented their own rock. And this single innovation would unlock two very different ways of building a city. First up, let's take a look at Mesopotamia, in modern-day Iraq, and see how they decided to use this powerful new technology. Over here, the big problem was fuel. Firing up a kiln takes a ton of wood, and wood was pretty scarce. This made fired bricks incredibly expensive compared to the plain old sun-dried kind. They were, for all intents and purposes, a luxury good. So they had to be smart about it. They didn't build entire structures out of these things. No way. Instead, they used these expensive, super durable bricks strategically, where it counted the most. For the foundations of buildings to resist moisture from the ground, and for the outer shell of their massive ziggurats, protecting a much cheaper core of sun-dried brick from the elements. It was a brilliant way to build these huge monuments that screamed power and permanence.
And the absolute peak of this idea has to be the Ishtar Gate of Babylon. I mean, just look at it. Here, the brick isn't just a structural element anymore, it's a canvas. It's glazed in these brilliant blues and molded with these intricate reliefs of lions and dragons. This wasn't just a gate, it was a powerful statement of imperial might and divine favor, engineered to last for an eternity.
Okay, now let's hit the brakes and go somewhere completely different. Let's talk about the Indus Valley, because their whole philosophy was the polar opposite.
The first thing you have to understand about the Indus Valley is this incredible ratio, 1 to 2 to 4. That was the dimension of their bricks. And what is absolutely mind-blowing is that they were all like that, across a territory of 1 million square kilometers. The level of coordination and central planning that required is just staggering. And this really gets to the core of the difference. In the Indus Valley, the fired brick wasn't saved for kings and gods. It wasn't for showing off. It was a tool for the public good, and they used it on a massive civic scale.
So what did they do with it? They built the world's first sophisticated urban sanitation system. They used the water-resistant properties of fired ceramic to create these huge public baths, to line wells for clean drinking water, and, most incredibly, to build these elaborate covered drainage systems to carry away waste. You could never do this with sun-dried brick. It would just turn back to mush.
And you have to think about what that means for a city. This advanced public health engineering made their cities cleaner, healthier, and just plain safer. It cut down on the risk of disease that always comes with early urbanization, and that allowed for these large, dense populations to thrive, even in a tropical climate. It was a massive investment in the health of the people. So there you have it. One single piece of technology, the fired brick, but two totally different blueprints for how to build a civilization with it. You really see two clear paths emerge. On one hand, you've got Mesopotamia, using the brick for prestige, creating these monumental structures that projected state power. And on the other hand, you have the Indus Valley, using it for public utility, creating mass-scale civic works that enabled a healthy, dense urban life. One path was about art and propaganda, the other was about standardization and public health. And that is really the big takeaway here. The invention of the fired brick, this man-made stone, was about so much more than just building walls. It was the technology that allowed humans to finally defeat the forces of decay and build lasting, dense, complex societies. It's what made the city, as we know it, possible.
You know, when we look at ancient pottery, we usually see art or maybe history. But what if I told you that locked inside these beautiful objects is a whole other story? A story of advanced chemistry, sophisticated engineering, and the absolute mastery of fire. Let's uncover the hidden science of how these ancient artisans were able to literally paint with fire itself. Okay, so take a look at this stunning Greek vase. It looks like it's been painted with some kind of permanent black ink or pigment, right? Well, not quite. The truth involves a process so precise, it's actually been compared to modern nanotechnology. And it reveals how these ancient artisans were also just brilliant scientists.
So here's our game plan. We're going to start with the basic quest for heat, then uncover the chemical miracle behind Greek pottery. And after that, we'll dive into the massive industrial scale of Rome's ceramic empire. You're going to see how two different civilizations took the exact same material, clay, and just pushed it to its absolute limits.
All right, our story begins with the single biggest challenge for any ancient potter: heat. See, you can't just make a pot, you have to completely transform it with fire. And figuring out how to control that fire, well, that was the first great technological hurdle they had to clear. I mean, imagine digging a hole in the ground, piling your carefully crafted pots inside, and then just lighting a bonfire right on top. That's pit firing. As you can guess, the heat was super uneven, the temperatures were pretty low, and a huge number of your pieces would just crack or break. The stuff that did survive was porous and not very strong. It was a start, but man, was it inefficient. So obviously, they needed an upgrade. Innovation was a must. Potters eventually moved from those simple pit fires to the first real kiln, the updraft kiln, which gave them much better temperature control. Later on, cultures like the Romans went on to perfect the downdraft kiln, which was a true game changer in the world of pyrotechnology. So let's look at the physics here, because it's really clever. An updraft kiln makes sense. Heat rises. But it's also incredibly wasteful, since all that precious energy just rushes right out the top. The genius of the downdraft kiln is how it forces the heat to circulate all the way through the chamber before it can exit. This traps the energy, creating really even temperatures and maximizing fuel. This was the key to making high-quality ceramics consistently. So, with control over the heat finally established, we can get to the heart of the Greek miracle. Their famous black and red pottery wasn't just the product of a better kiln. It was the result of mastering the actual chemistry of the fire itself. The Greeks developed this amazing technique called three-phase firing. The paint they used was just a very fine, watery clay that was rich in iron. It's called a slip. The magic wasn't in the paint, but in how they could manipulate the kiln's atmosphere, basically the amount of oxygen available to the fire, to permanently change the color of that slip. Okay, let's break this down because it's absolutely incredible. First, with plenty of oxygen in the kiln, the whole pot turns red. The iron in the clay basically rusts. Then, the potter deliberately starves the kiln of oxygen. They'd throw in green wood to make a ton of smoke. This smoky atmosphere strips the oxygen from the iron, turning the entire pot black. Now here's the key part. At this higher temperature, that ultra-fine slip melts just enough to seal itself, becoming non-porous. So, in the final phase, they let oxygen back in. The body of the pot, which is still porous, soaks up the oxygen and turns red again. But the slip, the design, is now sealed. It can't reoxidize. It's locked in its black state permanently. And this wasn't just guesswork. This was real empirical science, perfected over generations. These potters had to control temperature and atmosphere with incredible precision. In fact, modern analysis has shown that the particles in that slip are so fine and the layers are so thin that it really is a form of ancient nanotechnology. Just mind-blowing. So while the Greeks were off perfecting this intricate chemistry for their art, the Romans were facing a completely different challenge. How do you supply a massive, sprawling empire? Their focus shifted away from chemical artistry and towards industrial scale. And that brings us to terra sigillata, or stamped earth. This was the iconic glossy red tableware you'd find on tables from Britain all the way to Syria. You can think of it as the Roman equivalent of a global brand, and its production was a true marvel of industrial engineering. The Romans used a similar slip technology to the Greeks, but they totally streamlined it for efficiency. They'd mix clay with water, let it all settle, and then they would carefully siphon off just the top layer, which contained only the very finest particles. When this stuff was fired, it would automatically vitrify or turn glass-like. It created that signature glossy waterproof finish all by itself, no polishing needed. And this is where the Roman genius for scale becomes truly mind-boggling. At production centers in places like Gaul, archaeologists have found enormous kilns, complete with sophisticated piping to distribute heat evenly, that could fire up to 40,000 vessels in a single batch. This wasn't a workshop, it was a factory. So what we have here are two ancient superpowers, both of them masters of ceramics, but with fundamentally different goals. The Greeks were pursuing chemical perfection, while the Romans were all about industrial perfection. The contrast is pretty stark, right? For the Greeks, the primary goal was all about aesthetic chemistry. Their key innovation was that incredible three-phase firing process. The whole method was chemical transformation, leaving a legacy of artistic masterpieces. For the Romans, the goal was mass production and branding. Their innovation was industrial kilns and logistics. Their method was standardization and scale, and their legacy was creating the tableware for an entire empire. So what's the legacy of this whole journey into the fire? Well, it's a really powerful story about human ingenuity, and it shows how technology evolves to meet completely different challenges. Ultimately, both civilizations were absolute masters of their craft. The Greeks achieved this almost magical control over the kiln's atmosphere to create timeless art. The Romans engineered massive, efficient systems to build an entire industry. And whether the goal was a single perfect piece of art or tableware for a whole empire, both paths represent a profound understanding of materials science that was basically unrivaled for centuries. So here's a question for you. What in the world connects ancient alchemy to modern nanotechnology?
I mean, it sounds like a riddle, right? One is this mystical, ancient quest to transform elements, and the other is this super cutting-edge field of science. But believe it or not, the answer is hiding in the shimmer of a 1,000-year-old piece of pottery. And that connection, that's what we're going to unpack today.
All right, so our story really kicks off with a classic problem: wanting something beautiful that you just can't have. It's a perfect example of how innovation is so often born out of frustration, you know? It's a challenge that really pushed these ancient artisans to their absolute creative limits.
I want you to picture this. It's the 9th century in Baghdad, which is the booming heart of the Abbasid Caliphate. Trade routes are bustling, and along with all the silks and spices, this stunning new luxury good starts showing up from Tang Dynasty China, this brilliant, pure white porcelain. It was totally unlike anything the local potters had ever seen, and the rich and powerful, they were absolutely obsessed with it.
So you've got this huge problem, right? On one hand, you have this perfect Chinese porcelain. It's pure white because it's made from these special kaolin rich clays. But on the other hand, the local Iraqi clay was, well, it was yellowish, kind of muddy. It just didn't have the right minerals. So the big question was, how could they possibly compete? Well, the answer was simple. If you can't make it, you gotta fake it. And what came next was honestly one of the most clever workarounds in the entire history of material science. It was a brilliant white lie that would literally change the world of ceramics forever.
So what did they come up with? It was this game-changing technology called a tin opacified glaze. See, the potters in Iraq figured out that if they added tin oxide to a pretty standard lead glaze, they could create this flawless, totally opaque white coating. It was a massive leap forward in chemical engineering.
Okay, so here's how they pulled it off. The recipe looks simple, but the chemistry is just brilliant. First, you'd start with your basic pot made from that yellowish local clay. Then, you'd coat it with this special glaze, the lead mixed with tin oxide. And finally, you fire it. The heat in the kiln works its magic, and what comes out is a pot that, to the naked eye, looks exactly like pristine Chinese porcelain. Just like that, the porcelain problem was solved. And you know, an idea this good, it wasn't going to stay local for long. I mean, just look at this timeline. It was invented in 9th century Iraq, and then it just exploded. By the 10th century, it's in Egypt and North Africa. By the 12th, it hits Spain. And from there, it actually becomes the foundational technology for some of Europe's most famous styles, like Majolica in Italy, and, get this, the iconic blue and white Delftware from the Netherlands. All from this one Iraqi invention.
But here's the thing, just copying porcelain wasn't enough for these artisans. The next big innovation wasn't about imitation at all. It was about creating something totally new. And this is where the story gets, well, a little mystical and dives into the world of alchemy. Yeah, this quote really says it all. Lusterware was the absolute pinnacle. It produced this metallic, iridescent shimmer that looked like it was made of pure gold or silver. The process was so difficult and so mysterious that people really saw its creation as a form of transmutation. You know, turning one material into another, which was the central goal of alchemy. Now, this process was super risky, and the knowledge was a closely guarded secret passed down in just a few families. First, you'd fire a pot with a normal glaze. Then, you'd paint on this special paste made of metal salts, like copper or silver oxides, mixed with stuff like sulfur and ochre. But the real secret, the magic, was in the second firing. You'd put it back in the kiln at a lower temperature, but this time, and this is crucial, you'd starve the kiln of oxygen. So what is actually happening inside that oxygen-starved kiln? Well, it's some remarkable chemistry. The super hot, oxygen-hungry atmosphere inside the kiln literally rips the oxygen atoms away from the metal oxides in that paste you painted on. And what you're left with is, honestly, it's mind-blowing. Once that oxygen is gone, what's left behind is a microscopically thin film of pure metal. We're talking pure copper or pure silver, suspended right there on the surface of the glaze. But here's the kicker. They're not just little flakes of metal. They are nanoparticles. And when I say nano, I really, really mean it. These particles were just a few nanometers thick. A nanometer is a billionth of a meter. To give you some perspective, a single sheet of paper is about 100,000 nanometers thick. This is the kind of engineering we associate with high-tech labs today, not medieval kilns. So think about that. This was, for all intents and purposes, the world's first practical use of nanotechnology. Those tiny nanoparticles didn't just reflect light like a mirror. They were so small, they actually diffracted it, bending the light waves to create that signature, magical, shimmering effect.
Without even knowing the physics, ancient alchemists had stumbled upon quantum effects. It's incredible.
Okay, so it's easy to think that all this incredible innovation was just flowing out of the Islamic world, right? Well, the story has this fantastic twist. It turns out the flow of ideas and materials was actually a two-way street.
So we know part one of the story. The potters in Baghdad were chasing that pure, brilliant white of Chinese porcelain. That was their obsession. But here's the flip side. At the exact same time, the master potters in China had an obsession of their own. And what they wanted more than anything was a vibrant, rich blue pigment they could only get from one place, Persia. In fact, this pigment was so famous for where it came from that in China, they literally called it Hui Hui Qing, which translates to Muslim blue. And the source of this incredible color was cobalt, which was mined in Persia. And it all comes down to the chemistry, which is why this stuff was so valuable. The imported Persian cobalt was rich in iron, and when you fired it, that iron created what they called a heaped and piled effect, these beautiful prized dark spots where the blue was thickest. Later on, when China found its own cobalt, it was higher in manganese, and it just produced a softer, kind of grayish blue. It just wasn't the same.
So let's step back for a second. When you put all the pieces together, you've got Persian cobalt traveling east to China, and you have Chinese porcelain traveling west to Baghdad, sparking all these new inventions. What you're really looking at is one of the very first examples of a truly global supply chain, all connected by the Silk Road.
So back in 18th century Europe, there was this absolute craze for a mysterious, almost magical material coming out of China. The French even had a name for it, maladie de porcelaine, the porcelain fever. It was a full-blown addiction that drove the rich and powerful to do some pretty wild things. And when I say wild, I mean it. Check this out. In 1717, Augustus the Strong, the King of Poland, made one of the most unbelievable trades in history. He gave the King of Prussia 600 of his best soldiers for just 151 pieces of Chinese porcelain.
That's the question, right? It sounds completely insane. Why trade real military power for a bunch of fragile vases? Well, to get it, you have to understand that this wasn't just pottery. This was high-tech stuff that the entire Western world was completely failing to replicate. The secret to all of this starts deep in the earth, in the very specific geology of a city in China called Jingdezhen. They've been perfecting this craft since way back in the 10th century. So here's the secret recipe. It had two key ingredients that were only found there. First, you have kaolin, a super pure white clay. Think of this as the bones of the porcelain. Then you add potunce, a special kind of rock that's the flesh. When you fire these two together at crazy high temperatures, the potunce melts into a kind of natural glass.
And that process, that fusion, is called vitrification. The two materials would completely merge, creating something entirely new. It had the delicate see-through quality of glass, but it was as hard and strong as stone. I mean, that was the magic trick Europe just could not figure. Okay, so they had the secret formula, but having a recipe is one thing. Turning it into a massive global export industry is something else entirely. How on earth did Jingdezhen pump out millions of these perfect pieces?
Well, the answer was this revolutionary piece of technology called the Long Yao, which literally means dragon kiln. And trust me, this thing was way more than just an oven. It was an engineering masterpiece that made mass production possible.
And when I say mass production, I mean it. These kilns were absolutely enormous. We're talking about a huge tunnel built straight up the side of a hill, stretching up to 60 meters long. That's more than half a football field. And the capacity was just staggering. A single firing in one of these dragon kilns could bake up to 25,000 individual pieces of pottery at once. 25,000. The scale is almost hard to wrap your head around.
And the design itself was pure genius. Because it was built on a slope, the whole kiln acted like a giant chimney. You'd light a fire at the bottom, and this powerful natural draft would just suck the hot air all the way up, creating the intense, super hot temperatures needed for that vitrification we talked about. It was incredibly efficient.
Now, the dragon kiln was the heart of the operation, but it was part of a much, much bigger industrial machine. The entire city of Jingdezhen and the area around it, it was all built for one single purpose: making porcelain.
You see, to feed these giant kilns, the mining operations for that special clay had to be just as massive. They were digging quarrying pits 50 meters deep.
It was so intense that Galling Mountain, the very source of the calling clay, was mined so relentlessly that parts of it literally collapsed.
So when you put it all together, the specialized jobs, the mass production, the huge-scale mining, you realize that Jingdezhen was, for all intents and purposes, the world's first true industrial city. And this was all happening centuries before the Industrial Revolution even kicked off in Europe.
Okay, so now we can finally connect all of this. The secret recipe, the incredible technology, back to that wild trade we started with. Now we can really understand why Europeans called this stuff white gold.
Just look at the difference here. On one side, you've got China using its unique kaolin and Petunse formula to make this strong, beautiful, translucent material. On the other side, you've got European potters messing around with soft clays in what one source calls a struggle to imitate whiteness. Their stuff was cloudy, it was fragile, it wasn't even in the same league. And that's the absolute key to this whole story. Europe wasn't just importing pretty cups and vases. They were importing the product of a secret formula and a manufacturing process that was centuries ahead of theirs. China had a complete technological monopoly. And suddenly, that trade of 600 elite soldiers, it makes perfect sense. Augustus the Strong wasn't just buying fancy decorations. He was buying intel. He was buying physical examples of a rare and advanced technology, hoping his own people could reverse engineer it. He was trading military hardware for a technological secret.
So the story of porcelain isn't just about art history. It's a massive lesson in geopolitics. It shows you, plain and simple, how mastering a new material, how getting that technological edge translates directly into wealth and global power.
For centuries, Europeans were just captivated by this delicate yet super durable, brilliantly white porcelain that was being imported from China. It was like magic, you know? They had absolutely no idea how it was made. And this one object of desire, it launched multiple desperate quests all across Europe to try and unlock its secrets. Okay, so our first quest kicks off not with a potter, but with a famous Florentine sculptor, a guy named Luca della Robbia. He looked at this whole ceramic puzzle and basically thought, what if the goal isn't to copy porcelain? What if it's to elevate something else entirely? See, Della Robbia's big idea was to take simple terracotta, which, by the way, literally just means baked earth, and give it the same brilliance and permanence as carved marble. If he could pull that off, he could create these huge, colorful sculptures that could finally withstand the weather outdoors. A total game changer. And you know what? He did it. He came up with this pretty revolutionary 4-step process. He used a very specific calcium-rich clay, fired it once, then coated it in this special glaze made of tin and lead. Then, a second firing fused that glaze into this brilliant, almost liquid-looking white surface that was completely weatherproof. Seriously, nothing like it had ever been seen before in European sculpture. And get this, his invention was so valuable, so groundbreaking, that his family guarded this secret formula for an entire century. They built a whole artistic dynasty on this one technical breakthrough. So from a closely guarded secret, we move on to a totally different kind of story. This was the first direct European attempt to actually crack the Chinese porcelain code. And this one had some serious money behind it. It was bankrolled by one of the most powerful families in history, the Medici of Florence. Now, since they didn't have the key ingredient, this special clay called kaolin, the Medici alchemists, and that's really what they were, tried to invent a substitute from scratch. They created what we now call a soft paste porcelain. It was this incredible mixture of white clay, a glassy material called frit, and even ground up rock crystal. I mean, this was pure chemical invention. And what's so wild here is just how close they got, and yet how incredibly far they were. On one hand, their soft paste porcelain looked translucent, almost like the real deal, but technically, it was kind of a disaster. It warped in the heat of the kiln, the glaze came out all cloudy, and it was so fragile you could literally scratch it with a knife. Their ambition was enormous, but the project was ultimately what you'd call a noble failure. Production just stopped when their patron, Grand Duke Francesco I, died, and with him, poof, the funding for this incredibly expensive experiment just vanished. Today, only about 60 pieces of this amazing effort are known to survive. And this brings us to our third and by far the most dramatic quest. We're heading to France now to meet a craftsman named Bernard Palissy, whose desperate search for perfection became the stuff of absolute legend.
Palissy started out as a glass painter, but he got completely obsessed with discovering the secret to white enamel, this smooth, glass-like coating that he thought could imitate the flawless look of porcelain. And this wasn't some weekend hobby, you know? This became a 16-year ordeal that brought him to the very brink of total ruin, just filled with one failed experiment after another. And this is where his obsession becomes legendary. The story goes that during one critical, all-or-nothing firing, he ran out of fuel. And in a total frenzy, he started feeding his own furniture and then even the floorboards of his house into the kiln just to keep it going. Now, whether that's literally true or not, his own writings confirm the struggle was agonizing and very, very real. And here is the beautiful, ironic twist in all of this. After all that struggle, he never figured out how to make Chinese-style porcelain. But instead, he discovered something entirely new, his famous rustic ware. These were these incredible ceramics decorated with hyper-realistic casts of snakes, lizards, and plants, all covered in these dazzling, brilliantly colored glazes. He failed at his goal, but he accidentally created his own unique, amazing art form. So, after all that, what do we take away from these three very different stories? Well, it seems like each one reveals something really crucial about the messy, unpredictable, and often frustrating process of innovation. What we really have here are three timeless models for innovation. First, you've got Della Robbia, the guarded secret, where you perfect what's already there and protect it. Then there's the Medici, the ambitious moonshot, the big project that fails but pushes the boundaries and shows us what might be possible. And finally, you've got Palissy, the obsessive discovery, the one who fails at their original goal but stumbles upon something even more valuable by accident. These aren't just historical tales. They're basically blueprints for how breakthroughs still happen today. I want you to think for a second. What do clean water, skyscrapers, and the light bulb all have in common? I mean, really think about it. What could possibly connect those three things? That's right. The unsung hero here is ceramics. We're gonna explore how turning simple clay from just a craft into a high-tech science actually enabled three massive revolutions that built the world we live in today. Okay, first up, let's take a trip back in time, back to the 19th century. We're heading to a city that was, and I mean this literally, drowning in its own waste. The situation was, well, it was dire. London was the biggest city on the planet, but its sanitation was basically medieval. You had cesspools just leaking raw sewage right into the groundwater. And the River Thames, it was the city's main source of drinking water and its main sewer. Yeah. The result was just one devastating cholera epidemic after another. This whole crisis came to a head in 1858 with something called the Great Stink. The smell was so bad that Parliament had to soak its curtains in chemicals just so they could get their work done. Unbelievable.
So the solution was a massive new sewer network. It was an absolute engineering marvel designed by Joseph Bazalgette. But here's the problem. What do you make the pipes out of? The early tunnels were made of brick, which is porous, so they just leaked everywhere. What Bazalgette needed was a brand new material. And you guessed it, that's where ceramics came in. And here is the brilliant solution. A manufacturer, a guy named Henry Dolton, perfected what's called the salt-glazed stoneware pipe. Now, unlike leaky brick, this stuff was completely waterproof. It was also chemically inert, which just means it wouldn't corrode over time, and that smooth glazed surface, it was a game changer, preventing the blockages that plagued all the older systems. You have to understand, at the time, no other material could give you this combination of strength, being waterproof, and being cheap enough to actually use. Dolton's factory just started churning out miles and miles of these pipes, creating the arteries for a brand new, much healthier London. But Dolton didn't stop there. He was on a roll. He took insights from Louis Pasteur's new research on bacteria and developed porous ceramic water filters. These things could physically trap deadly microbes. This was revolutionary. It meant genuinely safe drinking water for the first time ever on a mass scale. All right, so ceramics cleaned up our cities. Pretty amazing. But they also helped build them sky high. So let's move on to the next great revolution, the age of steel. Now, this is a really fascinating question. You know, the late 19th century was all about steel. Railroads, bridges, the first skyscrapers, they were all built with steel. But how do you actually make steel? Well, first, you have to figure out how to deal with unbelievable mind-melting heat. And the key to that is a special kind of ceramic called a refractory ceramic. Basically, these are materials designed to line furnaces and contain molten metal at temperatures that would just vaporize almost anything else. So think about that. Steel is literally born inside a ceramic shell. But here's where it gets really interesting. The Bessemer process, invented back in 1856, was this huge leap forward for making lots of steel. But it had one fatal flaw. The ceramic lining of the furnace, it was chemically acidic. The problem is that a major impurity in most iron ore, this stuff called phosphorus, is also acidic. And a little high school chemistry for you, acids don't react with other acids. So because the lining couldn't get rid of the phosphorus, the steel came out brittle and totally useless. This was a huge deal. It meant you could only use these rare, super expensive iron ores that didn't have much phosphorus in them. So here is the ingenious solution. In 1878, two cousins, Thomas and Gilchrist, had this revolutionary idea. They said, hey, what if we change the chemistry of the ceramic lining? Think of it like a magnet, right? You need opposite poles to attract. So they lined the furnace with basic dolomite bricks, another type of ceramic. And what happened? During the process, the basic lining reacted with the acidic phosphorus, pulling it right out of the iron and into a waste product called slag. Brilliant. And the impact of this one change was immediate, and it was global. Suddenly, all the world's vast deposits of cheap iron ore, the stuff full of phosphorus, were now usable. Steel became cheap, it became abundant, it became the primary material for building the modern world. And it was all thanks to just changing the type of ceramic brick inside a furnace. Incredible. Okay, so we've conquered sanitation, and we've built the steel skeleton of our cities. But now we have to power them. And this brings us to our final revolution, taming the invisible force of electricity. So early on, things like telegraph systems used glass insulators. And for the low voltages they were using, that was fine. But when engineers tried to send high voltage power over long distances, well, glass failed. And it failed spectacularly. It would attract moisture, which caused short circuits, and it was just too brittle to support those heavy copper cables. They needed something way, way tougher. The solution came from an inventor named Fred M. Locke. He developed something called wet process porcelain. What he did was mix clay into this kind of dough-like state and then fire it at super high temperatures. This created a material that was fully vitrified, which is a fancy way of saying it turned into a non-porous, glass-like substance, but one that was way, way stronger than regular glass. And Locke's design, it was just genius. The material itself was a perfect insulator. He then glazed it so it would shed water and dirt, but the really clever part was the shape. He designed them with these flared skirts, which they actually called petticoats. What they do is make the path longer. They dramatically increase the surface distance that electricity would have to travel to jump from the wire to the pole. This stopped those dangerous electrical arcs from happening. And the big test for this new ceramic technology? It was the monumental 1896 power line from Niagara Falls all the way to Buffalo. And it worked. It worked perfectly. For the very first time, massive amounts of electricity could be moved safely over huge distances. This was the birth of the electrical grid. This is what literally lit up the world. So let's pull all these threads together, shall we? You've got sanitation, steel, and electricity. 3 massive pillars of our modern world. And it turns out they are all resting on the very same foundation. Think about it. In each case, there was a specific problem that was holding back progress. You had leaky sewers, impure steel, short-circuiting power lines. And in every single case, the solution was a new kind of advanced ceramic, one that was engineered for a very specific purpose. It really was the hidden ingredient that made everything else possible. And you know, this stuff didn't just happen overnight. These breakthroughs were actually the result of almost 200 years of progress. It all started with perfecting fine porcelain way back in 1710. Then it moved to industrializing production with people like Wedgwood. And then, boom, it just exploded in the late 19th century with all these specialized uses we've been talking about. It was the slow, deliberate transformation of ceramics from a simple craft into a really sophisticated science. And we really have to give credit where it's due. Pioneers like Johann Friedrich Bucher and Josiah Wedgwood. These are the guys who turned pottery into an industrial science. They created the foundation of knowledge that people like Dalton, Thomas, and Locke would later use to literally change the world. What if I told you that that exact same class of material is what we use to stop armor-piercing bullets? It sounds crazy, I know. So today, let's dive into the absolutely wild story of how scientists and engineers turned one of the most brittle materials out there into a revolutionary shield. And that right there, that's the big question we're going to tackle. How did this happen? It's a journey that's going to take us from the atomic level, literally looking at bonds between atoms, all the way to the front lines of conflict. And it really shows how a simple need for stronger, lighter protection can spark some incredible innovation. All right, so our story really kicks into high gear right around the middle of the 20th century. You've got the Cold War, and the geopolitical tension is just off the charts. This created a frantic, no-holds-barred race for technological superiority. And, you guessed it, armor was a huge piece of that puzzle. You know, for centuries, the playbook for armor was simple. If you're facing a bigger threat, you just add more steel, thicker and thicker. But that brute force approach was starting to hit a wall. Projectiles were getting way faster, way more powerful. And all that steel? It was making vehicles too heavy, too slow, and just plain inefficient. It was clear that they desperately needed a totally new way of thinking about protection. And the Vietnam conflict is really where this problem went from theoretical to critical. I mean, in the dense jungles, mobility was everything. Helicopter crews, in particular, were just incredibly vulnerable to ground fire. But you can't just bolt tons of steel onto a helicopter, right? Every single pound messes with its lift, its range, its maneuverability. They needed something new, something light, and they needed it yesterday.
Okay, so this brings us to the core science. How in the world does a material we associate with being breakable stop a bullet? Well, the magic isn't in resisting the force, like you might think. It's about completely changing the rules of the game at the moment of impact. And to get that, we've got to zoom way, way in, down to the microscopic level. All right, here is the fundamental difference, the key to everything. In metals, you have electrons that are shared pretty loosely, which lets the atoms kind of slide past each other. That's what makes metal bendy or ductile. Ceramics, they are the complete opposite. Their atoms are locked into these super rigid bonds, either ionic or covalent. You could call it atomic stubbornness. They just refuse to deform. So, think about it like this. Steel armor is basically a catcher's mitt. It gives a little, it deforms, and it absorbs the energy of the ball over a bigger area. Ceramic armor? No way. It's more like a hammer hitting another hammer. It doesn't catch the projectile, it confronts it head-on and forces the projectile to shatter. It's a completely different philosophy of defense. And this whole confrontation happens in a flash, in a crucial 3-step process. First, you have what's called dwell. The instant the bullet hits, its tip is stopped dead in its tracks, just for a few microseconds. Second, shatter. Because the ceramic is so incredibly hard, way harder than the bullet, the projectile's own energy is turned back on itself, and the tip just disintegrates. And finally, disperse. Whatever energy is left over gets spread out across the entire ceramic plate, kind of like ripples in a pond, and that prevents it from penetrating through. Now, it's not like there's just one kind of ceramic armor. You wouldn't use the same tool for every single job, right? Well, engineers feel the same way. They've developed a whole toolkit of different ceramic materials. And a good way to think about it is like a pyramid of protection. And this is where we get into the constant balancing act of engineering. It's always a trade-off. Do you need the absolute best, top-tier performance or the lightest possible weight? Or do you need something that's affordable enough to make tons of? The answer to that question is what determines which ceramic you're going to choose. Okay, so at the base of our pyramid, we've got alumina, or aluminum oxide. This is the workhorse. It's the densest of the big three, coming in at about 3.9 grams per cubic centimeter. But, and this is the important part, it's also the cheapest and easiest to manufacture. So that makes it the go-to for things like vehicle armor, where adding a little extra weight isn't a total deal breaker. All right, moving one step up the pyramid, we find silicon carbide. Now this stuff is lighter than alumina, and it gives you a big jump in ballistic performance. The catch? Of course, it costs more to make. This is your balanced choice, your middle ground. It's perfect for something like a light tactical vehicle where you need better protection, but you can't afford the massive weight penalty of just piling on more alumina. And then we get to the top, the apex of the pyramid. This is boron carbide, and this material is just remarkable. It's incredibly light, only 2.5 grams per cubic centimeter, which is actually lighter than aluminum, but it's also one of the hardest materials known to science. Yeah, it's extremely expensive, but when weight is the #1 enemy, like in personal body armor for soldiers or shielding for aircraft, it is absolutely 100% indispensable. And this table here really lays it all out, right? It shows that trade-off in action. As the density goes down and the performance goes up, the cost just skyrockets. Each one of these materials has its own sweet spot, optimized for a very specific job. So, we've established that ceramics are super hard and super light. Awesome. But what about that core problem we started with? Their fragility. I mean, stopping one bullet is great, but what happens when you're facing more than one threat? Well, engineers had to get really clever to solve this one.
And this really was the original Achilles heel. The early armor was often just a single solid plate, what they call a monolithic plate. The problem was, one hit could send cracks spiderwebbing across the whole thing. It would just destroy its structural integrity, leaving the wearer completely vulnerable to a second shot. You know, that single challenge drove decades of innovation. So back in the 80s, we started seeing the rise of composites. This is where they would embed tiny ceramic particles inside metal matrices, which gave you a mix of the ceramic's hardness and the metal's toughness. Fast forward to the 2000s, and we're talking about nano-engineering, actually manipulating the material at a molecular level to control how it fractures, and that dramatically improved its ability to take multiple hits.
So after all that, what's the big takeaway? What does this journey from atomic bonds to these super advanced composites really tell us? Well, for one, it shows that these materials are often the unsung heroes of our modern world.
And his quote just captures it perfectly. From armor shielding pilots in Vietnam to components in today's electric vehicles, ceramics serve as the silent sentinels of technological progress. I mean, think about that. The same class of material that was protecting helicopter crews all those years ago is now absolutely essential for things like the inverters in your electric car or components inside your smartphone. They really are these silent, invisible sentinels that enable so much of our tech.
This is a story about how that same simple material plays one of the most important roles in one of the most powerful technologies ever invented. The inside of a nuclear reactor is, well, it's just about the most hostile place you can imagine for any material. We're not talking about just being a little hot. We're talking about an environment literally designed to tear matter apart. So that's the big question, isn't it? In an environment that's actively trying to destroy everything inside it, what in the world could you possibly use to contain that kind of power? What can stand up to that kind of fury?
To find the answer, we have to really understand the problem. We need to step inside this nuclear crucible. We got to see exactly what we're up against. You see, inside that reactor core, it's not just one problem. It's a constant three-way assault. You've got intense atom-shattering radiation bombarding everything. You've got extreme chemical reactions trying to corrode it all. And on top of that, you have these massive, stressful swings in temperature. Almost any normal material would just fall apart.
And the answer? The thing that could take all that punishment? It wasn't some fancy sci-fi supermetal. Nope. It was good old ceramic. Specifically, ceramic uranium dioxide. It really is the quiet, unsung hero of the entire atomic age. And this chart right here, it tells you everything you need to know. The first reactors used metallic uranium, but just look at the difference. The ceramic version's melting point is more than double. And check this out. When you blast the metal with radiation, it swells up and gets deformed, which is incredibly dangerous. The ceramic, it just holds its shape. Let's just park on that number for a second. 2,847 degrees Celsius. To put that in perspective, that is way hotter than most lava. This incredible ability to take the heat is what gives reactor operators a massive safety margin. It's one of the key things helping to prevent a catastrophic meltdown. And it all comes down to this superpower called dimensional stability. See, when uranium atoms split, they create nasty fission gases. In the old metal fuel, those gases would form little bubbles that make the fuel swell up and break. But the ceramic's crystal structure acts like a tiny molecular cage. It actually traps those dangerous gas atoms right where they are, holding them safely for years. It's amazing. So these things are incredible. But how do you even make them? Well, it's a whole lot more complicated than throwing a pot. It's a high-tech process, a real triumph of ceramic engineering. It's really this elegant four-step dance. First, you grind uranium oxide into a superfine powder. Then you process that powder into slightly larger grains. Step 3, you press those grains with immense force into that classic little cylinder shape. But the final step, sintering, that's where the magic happens. You bake the pellets at a blistering 1,700 degrees Celsius, fusing all the grains together into an incredibly dense, hard ceramic. That becomes the very first line of defense against radioactivity.
But the story doesn't just stop at your local power plant. Oh no. During the Cold War, the race for nuclear dominance pushed this ceramic tech into some truly wild, out-there projects, testing it to its absolute breaking point.
This timeline really throws you right into the middle of the action.
We're in the 1950s and 60s, and the government is funding these incredibly bold, almost sci-fi experiments. You've got tests on advanced new fuel types, and then this, the idea of building a nuclear-powered jet bomber. I mean, the ambition here was just off the charts. Experiments like Borax IV showed that you could make even more advanced ceramic fuels, and that research fed directly into this wild idea, the Aircraft Nuclear Propulsion Program. The goal, a jet bomber that could stay in the air for weeks, even months, powered by a tiny nuclear reactor that had to run at the same temperature as a jet engine. The ceramic components had to be tough beyond belief. So the nuclear jet, it never actually flew. The program was canceled in 1961. But here's the thing. It wasn't a total loss, not even close. The incredible material science breakthroughs they had to make just to try and build that impossible engine, none of that was wasted. It laid the foundation for the next generation of advanced reactors we're still designing today.
Okay, so ceramics can tame the nuclear reaction. They can handle these insane, extreme conditions. But that leaves us with one last massive challenge. What do you do with the leftover waste that stays radioactive for thousands and thousands of years?
For a long time now, the standard solution has been to melt nuclear waste down with glass, basically encasing it in something called borosilicate glass. And look, it's a pretty good solution, but it's not perfect. And it turns out that, once again, a special kind of ceramic offers a much better answer. And that answer is called synrock. The name literally means synthetic rock, and that is the perfect description. It's a special ceramic that's engineered to copy natural rocks that have been sitting in the Earth's crust for millions of years, safely locking away radioactive elements the whole time. Nature already solved the problem, we just copied the recipe.
So how does this actually work? This is the truly brilliant part. Instead of just putting a glass box around the waste, synrock builds a prison for it at the atomic level. It uses this cool principle where different atoms can swap places with each other in a crystal. So it basically tricks the radioactive atoms into becoming part of its own super stable crystal structure. They are locked in tight, creating a final solid that is unbelievably resistant to being broken down by groundwater even over millions of years.
You know, space is just the ultimate hostile environment. It's not just the cold or the vacuum, it's the unbelievable violence of getting there and especially coming back. And conquering those extremes, it's not just about bigger rockets. It's about a hidden revolution in material science. So let's dive into the incredible ceramics that literally make spaceflight possible. All right, let's kick things off with maybe the most iconic challenge of them all. Picture this, a spacecraft screaming back into our atmosphere at Mach 25. That's 25 times the speed of sound. It's hitting a wall of air so hard that the air itself turns into a superheated plasma. So how on earth does anything survive that fiery plunge? This was the absolute make or break problem for the Space Shuttle program. They didn't just need a shield that could survive an inferno once, they needed one that could do it over and over again for the next mission. And this slide really puts into perspective the huge engineering leap that was required. The old Apollo capsules, they used what are called ablative shields. Basically, they were designed to burn away, sacrificing themselves layer by layer to protect the astronauts inside. But the shuttle was supposed to be a reusable space plane. You couldn't just bolt on a new shield after every single flight. The solution had to be something totally different. Let's just hang on this number for a second, Mach 25. That kind of speed generates an immense amount of energy that you have to manage. And, you know, a common misconception is that it's friction. It's not. It's actually the insane compression of the air right in front of the vehicle that creates all that incredible heat. And that heat is just staggering. The surface of the shuttle could hit 1,650 degrees Celsius. That's 3,000 degrees Fahrenheit. To give you some perspective, that is hotter than the melting point of steel. The shuttle's aluminum skin would have just, poof, vanished. And the solution, as you see here, was these HRSI tiles. Now, these weren't just solid blocks of ceramic, like you might imagine. They were something way cleverer, made from the same basic thing as sand, super high-purity silica. Okay, here's the part that just blows my mind. The main type of tile they used, called Li900, was 90% air. It was basically a rigid sponge made of pure silica fibers. And that extreme porosity, that was the secret to its power. See, trapped air is a terrible conductor of heat. It's one of the best insulators there is. You could actually heat one of these tiles until it was glowing red hot and still pick it up by the edges with your bare hands. It's incredible. But that porous silica was super fragile, so the tiles got their iconic black coating.
this special glass had two absolutely critical jobs. First, it gave them a tough, waterproof skin. But second, and this is crucial, its black surface was incredibly efficient at radiating all that re-entry heat right back out into space. It acted like a perfect radiator, just beaming the energy away.
So we figured out how to protect a spacecraft from the heat on the outside. But what about the controlled explosion happening on the inside, in the rocket engine itself?
Yeah, this is a whole different ballgame. Inside a rocket engine, you don't just have crazy high temperatures. You have immense pressure, extreme thermal shock, going from nearly absolute zero to thousands of degrees in seconds, and you have super corrosive chemicals flying around. An insulator, like one of those silica tiles, it would be torn to shreds in an instant. So you need a different kind of material hero for this job. Enter silicon nitride. Now, what's so special about it? Well, unlike metals, which get soft and weak when they get really hot, this advanced ceramic just keeps its strength and toughness at unbelievably high temperatures. I mean, just look at how versatile this stuff is. It holds its strength way past 1,000 degrees Celsius, which makes it perfect for rocket nozzles and thrusters, like the ones on Japan's Akasuti space probe. But it also resists that thermal shock so well that it was used in the cryogenic pump bearings of the shuttle's main engines, going from brutally cold to brutally hot without shattering. So let's just do a quick recap. For the massive insulation challenge of re-entry, we've got silica tiles, which are basically made of air. For the violent, high-strength challenge of combustion, we have super tough silicon nitride. But what about the next frontier? What happens when you combine those challenges and, well, turn the dial up to 11? And that brings us to hypersonic flight, flying at speeds above Mach 5, but still inside the atmosphere. And here, the engineering problems just get even more extreme. At these hypersonic speeds, the heat on the sharp leading edges of the wings and the nose cone can shoot past 2,000 degrees Celsius. And at that temperature, even those amazing silica tiles from the shuttle would soften and fail. You need something that can handle heat that is just completely off the charts. To solve this, scientists had to turn to a class of materials that almost defy belief. I mean, for all practical purposes, in this context, they're basically unmeltable. These are the ultra-high temperature ceramics, or UHCs. We're talking about materials like hafnium diboride that have melting points above 3,200 degrees Celsius. They are some of the most heat-resistant substances that we even know how to make. And this is where it gets really interesting, almost like a paradox. You'd think, for a sharp nose cone, you'd want the best insulator passable, right, to block the heat? Well, it turns out, no. UHTCs actually have high thermal conductivity, kind of like a metal. This lets them take that incredibly intense, focused heat right at the very tip and quickly conduct it away, spreading it out over a much larger area. It wicks the heat away before it can cause a localized meltdown. But even if they don't melt, they can still burn or oxidize in that hypersonic plasma. So engineers added another brilliant trick. They mix in some silicon carbide with the UHTC. Now, when that extreme heat hits, the silicon carbide right on the surface oxidizes first, and it forms a thin, protective layer of, you guessed it, glass. This glassy layer then seals the material underneath, protecting it from any more attacks. The material literally heals itself in real time.
Today, we're going to pull back the curtain on the secret foundation of our entire digital world. We're talking about a material you use every single second of the day, but you've probably never even seen it. Let's dive in.
Okay, so if I ask you a question like that, what's the first thing that pops into your head? You know, what's that one material that we all connect with computers, smartphones, all that high-tech stuff? Yeah, you got it. It's silicon, right? I mean, we named a whole valley after the stuff. Silicon gets all the credit, all the headlines, all the glory. It's the undisputed star of the show. But what if I told you that star is totally lost without the stage it performs on? That's right. The real unsung hero of the entire electronics revolution isn't some flashy semiconductor, it's humble ceramics. All right, so let's set the stage, literally. How in the world did this simple material become the actual foundation for everything we do in our digital lives?
This quote just hits the nail on the head, doesn't it? Silicon is the brilliant actor. That's the transistor, right? It's performing these unbelievable feats of calculation. But you know, every great actor needs a stage. And that stage was, and in many cases still is, a very specific kind of ceramic.
And that ceramic has a name, alumina, or, aluminum oxide if you want to get technical. It's the bedrock, the substrate, the very thing that holds those delicate integrated circuits in place. So why this stuff? What makes it so special?
Well, it has these three superpowers that were the perfect solution to the biggest headaches in early electronics. First, its high electrical resistivity means it's a fantastic insulator, so it keeps all those little electrical pathways from shorting out. Second, it has really good thermal conductivity, which means it pulls dangerous heat away from the silicon chip. And finally, its dimensional stability is just excellent. It doesn't warp or bend when it gets hot, which stops those tiny circuits from cracking. It's the whole package.
So you see, it's this perfect partnership, right? Silicon, the star, gets to do all the thinking and the processing. But Illumina, the stage, it's doing all the crucial behind-the-scenes work, keeping the star cool, keeping it stable, and making sure it's structurally sound. You take away that stage, and the whole show is over.
Okay, so ceramics gave us the foundation, but pretty quickly a new problem popped up. How do you protect the incredibly fragile star of the show from, well, everything else?
You know, a silicon chip is this tiny little miracle of engineering, but it's also super fragile. Even the tiniest bit of moisture in the air can cause corrosion and total, catastrophic failure. And this was a huge deal, especially for things like military and aerospace hardware that had to be absolutely reliable.
What they needed was a perfect seal, a totally airtight one. They called it a hermetic seal. Just think of it like microscopic armor for the chip, shielding it from all the bad stuff out there. The big question was, what material could you possibly use to build it?
And guess what the answer was? Yep, you got it, ceramics again. This thing, called the Ceramic Dual Inline Package, or CDIP for short, was invented over at Fairchild Semiconductor. It used a ceramic base and a ceramic lid, and they were sealed together with glass to create this perfect little hermetic fortress around the silicon chip. And look, this wasn't just some clever engineering trick. No way. This built an entire industry. The demand for these super high-quality, high-reliability ceramic packages was absolutely immense, and it was the driving force behind the growth of giants like Kyocera. In fact, Kyocera stands for Kyoto Ceramic Company. They saw the need and basically became the best in the world at supplying this stuff.
All right, so we've got a stable stage? Check. We've got a protective shell? Check. What's next? Well, the need for speed. How do you get signals to travel faster and faster without getting all messed up along the way?
So, the early packages used something called high-temperature co-fired ceramics, or HTCC. They were really strong, but you had to bake them at these insane temperatures, over 1500 degrees Celsius. And that was a big problem, because at that kind of heat, you could only use kind of mediocre conductor metals like tungsten. And those have higher resistance, which really slows down the signals. But then came the breakthrough: low-temperature co-fired ceramics, or LTCC. By adding glass into the ceramic mix, they could bake it at a much cooler temperature, below 900 degrees. And that simple change was a total game changer. It meant engineers could suddenly use amazing conductors like gold, silver, and copper that dropped the resistance way down and paved the way for the super high-speed signals that power everything today, from your 5G phone to advanced military radar.
And that brings us to the last part of our story. And honestly, this might be the wildest part of all: the relentless, unstoppable march of miniaturization. How do you possibly cram the power of a computer that used to fill a room into something you can just slide into your pocket?
Let's just start with a number that'll blow your mind. Over 1,000. That's roughly how many of these little things called multi-layer ceramic capacitors, or MLCCs, are crammed inside a single modern smartphone. More than 1,000 of them. They're absolutely essential for things like regulating power and filtering signals. But how on earth do you fit that many in one tiny device?
Well, you make them unbelievably, ridiculously tiny. It's kind of like Moore's Law, but for these little ceramic guys. Back in the 80s, a standard capacitor was pretty chunky. But today, they can pack the same power into a component that is literally smaller than a single grain of sand. It's incredible.
So how is that even possible? Well, imagine you're building a skyscraper, but for ants. First, they take a ceramic slurry and cast it into this paper-thin sheet. Then, they print conductive metal layers right onto it. After that, they stack hundreds, literally hundreds of these printed layers on top of each other. And finally, the whole stack gets fired in a kiln and becomes one single, rock-solid component. I mean, this is straight-up nanotechnology. We're talking about hundreds of individual ceramic layers, and each one of them can be less than a single micron thick. That's thinner than a spider's web. This incredible density is what makes the entire world of portable electronics even possible.
So that brings us right back to the beginning, doesn't it? After seeing everything this material has done, I think it's about time we give this hero the credit it deserves.
So, why does any of this matter? Well, think about it. Without ceramics, the silicon revolution as we know it might never have even happened.
They provided that stable stage. They built the protective armor for our circuits. They evolved to make lightning-fast communication possible, and they shrunk down to microscopic sizes to give us this incredible, portable world we live in today.
All right, let's get into it. Today, we're talking about the ceramic hero and how one single material basically unlocked the future of electric cars. It's a story about a hidden hero, a material that is completely rewriting the rules of what's possible for EVs. So get this, the key to the next generation of high-performance EVs, well, it started out as simple sandpaper. Seriously, a gritty, industrial abrasive. So how in the world did it go from the factory floor to powering our future on the highway? Okay, so to really get why this material is such a big deal, we gotta look at the problem it solved. For years, EV engineers were just stuck. They were hitting a major roadblock, this physical limit that we're gonna call the silicon wall. So here's the deal. You know the silicon that's in pretty much everything, our computers, our phones? Well, it turns out it just can't handle the heat, literally. When you're talking about the crazy high voltages and extreme temperatures needed for better electric cars, silicon just taps out. As we all started demanding more range and faster charging, silicon was overheating and wasting energy. It became super clear that if we wanted to take that next big leap, we were gonna need something new. And this is where our ceramic hero makes its grand entrance. Meet silicon carbide. You'll hear people call it SiC for short. And this stuff, this remarkable ceramic compound, is a total game changer for power electronics. I mean, the journey of this material is just incredible. It was discovered way back in the 1890s, and for the longest time, its only job was to be, well, gritty. It was used for sandpaper, grinding wheels, stuff like that. It took decades, literally decades, before scientists looked at the stuff and realized, wait a second, this could be a ridiculously powerful semiconductor. It's the ultimate underdog story, right? From the dusty factory floor straight into the heart of the most advanced cars on the planet. Okay, so what's the secret sauce here? What exactly gives SiC its superpowers? Why is it so much better for electric cars than good old silicon? Let's get into the science. The magic really comes down to this one concept. It's what's called a wide bandgap semiconductor. Okay, think of it like this. Imagine an electron is an athlete, and it needs to jump over a hurdle to start conducting electricity. For silicon, that hurdle's pretty low, easy to jump. But for silicon carbide, that hurdle is way, way higher. It takes a ton more energy to get that electron over the top, and what that means in the real world is that SiC can handle way higher voltages and temperatures before it even breaks a sweat. And look, you don't have to take my word for it. The numbers really do tell the whole story. The band gap, almost 3 times bigger than silicon. Thermal conductivity, how well it gets rid of heat, more than 3 times better. And this is the big one, the breakdown electric field. That's basically how much electrical force it can take before it fails. For SiC, it's a mind-blowing 10 times higher. It's not even in the same league. Yeah, let's just pause on that for a second. 10 times. For every 1 unit of electrical stress that silicon can handle, silicon carbide can take 10. This isn't just a little step up, it's a revolutionary leap. It's what allows engineers to totally rethink their designs, making things that are way smaller, much lighter, and just incredibly more efficient and powerful. So what does all this science actually mean for you, the driver? Well, it translates directly into the stuff we all care about. Because SiC is so darn efficient, way less energy gets wasted as heat. That means more of the battery's power actually goes to the wheels, which directly translates to more range. Plus, since it handles heat so well, you don't need these massive, heavy cooling systems. That makes the whole car lighter, which, you guessed it, makes it even more efficient. It's a win-win-win. So every hero needs that one moment, right? The moment they prove to the world what they can do. And for silicon carbide, that moment came when one very famous car company decided to go all in and make a massive bet on its potential. And of course, we're talking about Tesla and the Model 3. You see, before this, SiC was this kind of promising, cool tech, but nobody had really put it to the test in a high-volume car. Tesla was the first to take the leap and put it right at the heart of their vehicle. This was it, the moment the industry was forced to sit up and pay attention. So deep inside the Model 3's inverter, that's the brain that turns battery power into motion for the motor, there were 24 of these little silicon carbide power modules. And these tiny, compact powerhouses completely replaced the big, clunky, inefficient silicon parts from older designs. They literally changed the game. And making that one switch set off this incredible chain reaction. Okay, follow me here. You swap out the old silicon parts for new SiC ones. Right away, you're wasting way less energy as heat. Because there's less heat, you can shrink down the cooling system. And when you shrink the cooling system, you get a lighter, more efficient EV. It's this beautiful cycle of optimization, and it all started with choosing the right material.
But here's the thing, the Model 3's success wasn't just a win for Tesla. No way. It was a massive signal flare to the entire automotive industry. The hero had arrived, it had proven itself, and suddenly the path forward for electric cars was a whole lot clearer. After the Model 3 hit the streets, pretty much every other car maker on the planet had no choice but to start scrambling. They were all playing catch-up. Tesla had laid down the gauntlet, showing everyone what was possible. And just like that, silicon carbide went from being this interesting, niche material to an absolutely essential, non-negotiable part of any competitive EV.
Okay, so let's wrap this all up. What are the big takeaways? First, silicon carbide just blows past the old physical limits of silicon. Second, its scientific superpowers directly give us what we want: more range, faster charging. Third, the Tesla Model 3 was the proof in the pudding, showing it could work at a massive scale. And finally, SiC is now absolutely critical, a real cornerstone for the whole future of green energy. So think about this for a second. What could possibly link a high-tech dental implant with the smartphone you use every single day? One helps you eat, the other lets you scroll through social media. They seem like they're from completely different planets, right? Well, believe it or not, the answer is a family of materials called advanced ceramics. Now, I need you to forget everything you think you know about ceramics. We are not talking about coffee mugs or pottery class here. The stuff we're talking about is born in high-tech labs, engineered with incredible precision. So, first things first, let's totally shatter those old perceptions. Yeah, seriously, forget clay pots. These modern ceramics are designed to be unbelievably tough and chemically stable. We're talking about materials so robust, they can contain things like nuclear waste. And yet, they're so compatible with our biology that they can thrive in one of the most complex environments there is, the human body. And that ability to work inside us has just blown the doors open for this field called bioceramics. These materials have gone from being just, passive plugs to fill a hole, to active partners that actually help our bodies heal themselves. Okay, take a look at this. This really shows you the evolution of dental implants. For decades, titanium was the gold standard, right? But then comes zirconia, a ceramic so tough, they call it ceramic steel, and it completely changed the game. I mean, just look at the aesthetics. It's a huge win. No more of that gray shadow you can sometimes see through the gums, but the real magic is how your body reacts to it. Studies show zirconia attracts less plaque and causes less inflammation. It's not just a replacement part, it's a genuine upgrade for your body. Now, the absolute key to making any implant work is this process with a fancy name, osseointegration. It just means your living bone has to literally grow onto and fuse with the implant. At first, people worried if zirconia could do this as well as titanium, but the solution was brilliant. Engineers figured out how to create a micro roughness on the ceramic surface, basically giving your bone cells the perfect texture to grab onto and start building new bone. And this is where the story goes from just being cool science to something that feels like it's straight out of science fiction. What if the material wasn't meant to be permanent? What if it could just set up a temporary guide for your body's own incredible healing power and then get out of the way? Check out this incredible process. It's called bioresorption. Here's how it works. First, a porous ceramic scaffold gets placed into a bone defect. It's often made of something called hydroxyapatite, which is almost chemically identical to our own bone. That scaffold acts like a template, and new bone cells start growing all over it. Then, and this is the amazing part, as your new bone gets stronger, the ceramic scaffold just dissolves. It gets safely absorbed by your body until in the end, all that's left is your own natural healthy bone. The implant is just gone. And this isn't just a small step. This is the end game. As this quote gets at, this is the ultimate goal of regenerative medicine. You're not just patching a problem, you're creating a material that helps the body truly regenerate, does its job, and then gracefully disappears. Okay, so let's pivot. Let's leave the medical world behind and go back to that other object we talked about, the one that's probably within arm's reach of you right now. Let's talk about the super strong glass in your pocket. To really appreciate how tough your phone screen is, you have to ask a simple question first. Why is regular glass so ridiculously fragile? What's its fatal flaw? The answer is all on the surface. All glass, even perfectly clear glass, is covered in tiny, invisible flaws. And when you put any tension on that glass, by bending or dropping it, those little flaws are the starting points for cracks that can spread through the whole thing in an instant.
So, how in the world do you stop those cracks from ever getting started? Well, you use a seriously clever bit of chemistry called ion exchange. The whole idea is to create an invisible suit of armor on the surface of the glass. Here's how you make the shield. You take a sheet of this special glass and you dunk it into a crazy hot 400 degrees Celsius bath of molten potassium salt. At that temperature, all the smaller sodium ions inside the glass basically jump out, and larger potassium ions from the salt bath squeeze in to take their place. But because these new ions are bigger, they're packed in super tight, creating this immense compressive stress. It's like a tough, protective skin. For a crack to even think about starting, it has to first fight its way through that powerful shield. You know what's wild, though? The history behind this. The company Corning actually figured this technology out way back in the 1960s. They called it ChemCore, but for decades, it was basically a solution without a problem. It just sat on the shelf. Then, around 2006, a phone call from a certain company in California changed everything. And in 2007, the very first iPhone launched, and suddenly, this forgotten ceramic technology was protecting millions and then billions of screens all over the world. So we have these ceramics that can heal bone, and this ceramic glass that resists shattering. They seem completely unrelated, but they share this one common, invisible secret to why they're so incredibly strong. And that secret is compressive stress. That's it. It's this simple but incredibly powerful principle that ties these amazing materials together. Just think of it as a constant, invisible squeezing force that's always holding the material together and pushing back against damage. And look at how it solves both problems. For your phone screen, that engineered compressive skin is like a bodyguard that stops cracks before they can even get started. For that zirconia dental implant, its natural built-in strength and compression is what lets it stand up to the insane bite forces from chewing, day after day for years. It's the same invisible force, just solving two totally different problems. So here's the crucial point, the main takeaway from all of this. We are no longer just finding materials and figuring out what to do with them. We are deliberately engineering them, from the atoms up, designing them at a microscopic level to be tougher, smarter, and more integrated with our bodies than we ever dreamed was possible. The most advanced ceramics today, they're not just sitting on a shelf. They're active. They can heal themselves. They can adapt. They can even compute. Okay, so first things first, let's tackle the biggest, most obvious weakness of ceramics head-on, the fact that they crack. It's their Achilles heel, right? Well, scientists have figured out a way to turn that fatal flaw into an actual superpower. The big idea here is something called oxidation-induced self-healing. Now, I know that sounds super technical, like a mouthful, but the concept is actually beautiful in its simplicity. Instead of trying to fight against their environment, these new ceramics actually use the environment to fix themselves. So you're probably wondering, how on earth does that work? Let's walk through it. Picture this, a tiny microscopic crack forms deep inside the material. That crack exposes these brand new particles of something called silicon carbide. Now, when hot oxygen from the air, say inside a jet engine, rushes in and hits those particles, bam, a chemical reaction starts. It creates silicon dioxide, which is basically a type of glass. And this new glass material expands and literally fills the crack, like a kind of internal glue, sealing it shut from the inside. Now, here's the crucial part. This whole self-healing trick used to only work at insanely high temperatures, like way hotter than what you'd find in most real-world applications. But the real game changer, the big breakthrough, was adding these activators, things like manganese oxide. These little chemicals basically kickstart the healing process at lower, much more practical temperatures, like the kind you'd actually find inside a modern jet engine. This is what takes it from a cool lab experiment to something that's actually a practical reality. And why does this matter so much? Well, we're talking about making critical parts, like the blades inside a jet turbine, last way, way longer. That means aircraft become significantly safer and more efficient. It's just incredible. The material is taking the two things that used to be its worst enemies, heat and oxygen, and turning them into its own personal repair kit. Okay, so now we have this amazing self-healing material. Fantastic. But there is a problem. How do you actually shape it into all the complex parts we need? I mean, ceramics are famously, notoriously difficult to machine and work with. And that brings us to the next massive innovation:
3D printing. Think about how we used to make ceramic parts, the old school way, right? You'd need molds, and then you'd have to grind the piece into shape with diamond-tipped tools. It's slow, it's expensive, and you're pretty much limited to simple, solid shapes. Forget about anything too complex. But 3D printing, or what engineers call additive manufacturing, just flips the script completely. Instead of carving material away, you're building it up, layer by tiny layer. They use this special photosensitive liquid resin that's packed with ceramic powder. Then a UV light zaps it, hardening the resin exactly where it needs to be. This lets us create these mind-bendingly complex shapes like internal cooling channels or super lightweight lattice structures that were literally impossible to make before. Now, it's not a perfect science. Not yet anyway. One of the biggest challenges they're facing right now is printing with those darker ceramics, like the silicon carbide we were just talking about. The problem is, dark materials tend to absorb the UV light that's supposed to harden the resin. This makes it really tough to build up thick, solid layers. But, researchers are chipping away at that problem every single day. And once they crack that, the potential is just staggering. I mean, think about it. We could print origami-inspired metamaterials that get their strength from their clever geometry, not just from being a solid block. We could create lighter, way more efficient parts for hypersonic engines. Or even, get this, custom-fit medical implants that are so perfectly designed that your body just accepts them. All right, now let's make a pretty big pivot. We're gonna go from the very physical world of engines and implants to the digital world because, and you might not see this coming, it turns out that the entire future of artificial intelligence might depend on a very familiar type of ceramic, glass. So here's the problem Silicon Valley is facing. The giant, powerful chipsets needed to train today's AI models, they generate an absolutely insane amount of heat. And the plasticky, organic materials we use to package all those tiny components together, well, they're starting to buckle under the pressure. They warp, they fail. We're literally hitting a physical wall that's holding back the future of computing. The solution? Believe it or not, it's glass. Specifically, something called glass core substrates. So a substrate is like the foundation that all the tiny wires and transistors on a chip are built on. And if you look at the comparison, it's not even a contest. The organic stuff we use now, it warps when it gets hot. Glass, on the other hand, has amazing dimensional stability. It stays perfectly flat. And because it's so stable, engineers can print much, much finer and denser webs of wiring on it. So what? Well, denser wiring means data can zip between different parts of the chip faster, with less energy. That is the absolute key to making next-generation AI possible.
And look, this isn't just some tiny incremental improvement. This is the key. It's what unlocks our ability to build the next generation of AI hardware. By making the switch to glass, tech companies can finally create these enormous, incredibly complex system-in-package chipsets that are absolutely essential for training the powerful AIs of the future.
Okay, so let's just pull back for a second and look at the big picture here. We've talked about self-healing engines, 3D printed hypersonic parts, and glass substrates for AI. It might seem like a random bunch of cool tech, but it's not. This is all part of the next chapter in a really, really long story. I mean, look at this evolution. It really puts everything into perspective, doesn't it? We started out using ceramics as, basic enameled armor back in World War I. Then, during the space race, we used them to build heat shields that could survive re-entry. Fast forward to the digital age, and suddenly they're tiny little capacitors inside your smartphone. Today, they're the heart of electric vehicle inverters. And tomorrow, they'll be repairing themselves. So, what's the big takeaway? The fundamental shift is this. Ceramics are no longer just passive structural blocks. They're not just bricks and pots anymore. They have become active, functional systems that are at the very core of how our most advanced technology works. They've really become the invisible infrastructure of our daily lives. You know those tiny capacitors in your smartphone that manage the flow of electricity? That's ceramics. The crucial inverter in an electric car that turns battery power into motion? That's silicon carbide ceramic. Even those super strong, biocompatible dental implants? Yep, that's a ceramic called zirconia. The truth is, we are surrounded by and completely dependent on these advanced materials, and most of the time, we don't even know they're there. And all of this leads to a pretty cool final thought, right? Humanity's whole technological journey started with us learning how to shape stone and fire clay. And now, as we're staring down a future of self-repairing machines and unimaginable artificial intelligence, it seems pretty clear the Stone Age never actually ended. It just went high-tech.